Hello everyone. So today we will discuss about Doppler effect. Well, Doppler effect is caused due to the sound waves which move in the air. So let's say there's a train. The train is stationary, and there's a person standing at a distance x from the train. So let's say initially both the train as well as the person are stationary on the ground, and let's say the train blows its horn. So the person will hear the horn at a particular frequency. Now, as long as the train is stationary or the person is stationary, which means to say that as long as the distance between the person and the train is constant, which is x, the person will hear the horn or the sound of the train at a particular frequency. The frequency will not change. However, the moment that the distance between the train and the person standing on the ground starts to decrease or increase at a, let's say, at a constant rate or at a different rate, the frequency at which the person standing on the ground will hear the horn of the train will vary, and this phenomenon is called Doppler effect. Now let's consider the case in which the observer standing on the ground is stationary and the train, which is the source of sound, starts moving towards the observer, let's say at a velocity of or at a speed of u, right? And let's say the frequency of the sound which the train emits is let's say nu naught, and let's say the speed at which sound travels in air is v, right? So if the frequency of the sound emitted by the train is nu naught, then the time period will be what? Time period will be 1 by frequency, which is 1 by nu naught. It means what? That after every time t, the train will emit another wave, right? Now let's say the initial time t initial is equal to 0. So the time the time taken by the first wave to reach the observer will be what? That, let's say that time is equal to t1. So that will be distance traveled by the first wave divided by the velocity of sound, which is v, right? Now we have to find out after how much time the observer standing on the ground will hear the second wave. So when will the train emit the second wave? So the train will emit the second wave again after a time period t, which is 1 by nu naught, right? So the train will emit the second wave after a time period t, right? However, in that time capital T, the train would have moved a distance what in this direction? What distance the train would have moved? It would be u times capital T, the speed at which the train moves times the time. So the train would have moved a distance u times capital T. So the train would have reached somewhere around here, and this distance would be ut. So the new distance between the train and the observer would be what? X minus ut. So the new distance between the train and the observer would be x minus ut, and the time taken by the second wave then to reach the observer will be what? T means the time at which the second wave starts, the train emits the second wave, plus the time which the second wave takes to reach the observer, which will be new distance between the train and the observer divided by the speed of the wave. So the second wave will reach the observer at time t2 is equal to t plus capital T plus x minus ut by v. So the observer receives the first wave at time t is equal to t1 and the second wave at time t is equal to t2. So time difference between the waves which the observer observes is, let me call this t dash, which is equal to t2 minus t1. If I do this t2 minus t1, I will get v minus u divided by v into t. So t dash is the time difference between the consecutive waves which the observer hears. So in a way, t dash is the apparent time period of the wave, sound wave, which the observer hears. So the apparent frequency of the sound wave which the observer hears will be what? V dash is equal to 1 by t dash, will be equal to 1 by this whole term. And if we do this, we will get the apparent frequency as v divided by v minus u into nu naught. So we can see when the train moves towards, or when the source of sound moves towards the observer, the apparent frequency increases, right? because v by v minus u, so the denominator is smaller, so the numerator will increase, so the apparent frequency increases. Now, similarly, if the train moves away from the observer, then by the similar logic we will get v double dash is equal to v by v plus u into nu naught. So in that case, if the train moves away, the apparent frequency of the sound which the observer hears will increase, right? So this example was when the observer was stationary and the source was moving. Now let's consider the case when the source is stationary and the observer, let's say, moves towards the source, let's say at a speed of u. So in that case, the time interval, the time t1 at which the observer will hear the first wave, will be what? It will be distance x by the relative velocity. So since sound is coming from the horn in this direction at speed v and the observer is moving in this direction at speed u, so the relative velocity will be v plus u, and yeah, so this will be the time t1 at which this observer will hear the first sound. The time t2 when the observer will hear the second wave emitted by the source of sound will be what? Will be that time, as we saw earlier, the time period t after which the second wave will be emitted, plus the new distance between the observer and the source, which will be x minus ut divided by again the relative velocity between the sound wave and the speed of observer, which will be v plus u. Well, if you want to know more about the relative velocity, then you can always go through my previous video. I think in Newton's laws of motion, I had touched upon the concepts of relative velocity. When do the velocity add up, when do the velocity subtract? That will be helpful. So as we saw in the last exercise, the apparent time period of the sound wave which the observer hears will be what? T2 minus T1, and in that case T2 minus T1 will be what? It will be Vt divided by u plus v, and so the apparent frequency in this case will be v plus u divided by v into nu naught. So when the source moves towards the observer, the apparent frequency will again increase. The value will be v plus u divided by v into v naught, nu naught. And if the source moves away from the, if the observer moves away from the source producing the sound, in that case the apparent frequency which the observer hears will be what? V minus u divided by v into nu naught. So I have summarized all the observations which we have discussed towards the left side, and we can write a generalized form as follows. So the frequency which the observer will hear in a generalized form will be given by v, which is the speed of sound, plus u naught, which is the velocity or the speed of observer, divided by v minus us, which is the speed of source, into nu naught, which is the frequency of sound. Now please note that u naught, which is the speed of observer, it will be positive when the observer moves towards the source and negative when the observer moves away. Similarly, us, which is the speed of source, it will be positive when the source moves towards the observer and negative otherwise. So let's take this condition. In this condition, observer stationary. So it means what? U naught will be 0. Source moving towards observer. Source moving towards observer means what? It means that us will be positive. So in that case we get what? V is equal to nu is equal to, the frequency is equal to v by v minus us into nu naught, which is this relation. Similarly, this generalized form can be arrived at for all the other cases. So that's all I have in this video. Thanks for watching this video. If you have liked this, then please do subscribe to my channel. In the next video I will come up with some other interesting topics. Thank you.